Okay, you can hear me now, right?
Yes.
Okay, could you please turn the monitors to the lecture, so to the board? Okay. Yeah, it doesn't help if you can just go and tell, please. I see it over there. No, I mean the large monitors in front. Okay, I assume everything.
Excellent.
Yeah, everything is fine now, so let's get started. Now, in the previous lecture, we reached to some point of electrostatic interactions. And let me remind you, you now know why, in principle, you don't know the details, but you know why these particles here are this distance from each other. You know that this is because they have electrostatic repulsion. And this electrostatic repulsion can be expressed, kind of one parameter that we're going to use is the Debye counterionic atmosphere, the length of the Debye atmosphere. Now we have to go through the details of this lecture, which give us how exactly you relate the ionic concentration to the repulsive force. And then we have to actually consider how the electrostatic force relates to the van der Waals force, and both together determine the behavior of colloidal system. So this is the interesting stuff actually by the end of this lecture, which we have been doing all those complex theoretical lectures about, starting from the molecular interaction, going through van der Waals forces and electrostatics. Now, hopefully by the end of this lecture, you have the tools to apply these forces to real colloidal systems. And this is the case where the system is actually repulsive. Now, what happens if you add electrolyte? Decrease the Debye counterionic atmosphere, you are going to get your particles into something which looks like that. Aggregates of, usually they have this fractal structure, a little bit widespread. You can determine fractal dimensions and so on. The point is that obviously the particles don't always repel each other. And in this lecture, we want to understand when they change from repulsion to attraction and how does it work at all. How can you estimate this property? So let's start with some revision of what we have studied the previous time. We have the system of a charged surface, and you have two types of ions which are here in the liquid next to the surface. Now, first of all, you have the counter ions, which are of opposite charge to the surface, and they would like to really stick close to the surface. Now you have the co-ions, which come from the dissolved electrolyte, and the counter ions and the co-ions together form the counter ionic or the ionic atmosphere around the surface. So this atmosphere is the one which determines the electrostatic interactions. And then if you remember that this is fairly straightforward thermodynamics, the distribution of any ion would follow the Boltzmann distribution, where in the exponent we have the electrostatic energy of interaction between the ion and the surface and the thermal energy of any entity in the solution, including the ions. So what happens is the electrostatic interaction would like to bring the ions next to the surface. The thermal force, however, would like to spread them around and really kind of distribute them evenly. So depending on how strong the electrostatic force is, you can have the ions close to the surface or you can have them further out into the solution. If you plot the distribution of counter ions and co-ions, you are going to find out that the counter ions decay away from the surface, but they are more concentrated in the vicinity. And then the co-ions are actually depleted close to the surface, and then at infinity, both the concentration of counter ions and co-ions becomes the same. Now, we derive the following relation between the charge and the potential of the surface. The surface charge is related to the surface potential by the dielectric polarizability of the permittivity of the media, and this constant here, which is the Debye length, kappa. Actually, it is the inverse Debye length. And this is the definition of the Debye length that we derived in the previous lecture. And we discussed that the dimensions of these parameters are in inverse meters. So if you take 1 over this parameter, you have length. What we have here in the formulas are concentration and electrostatic parameters. Now, some of you have asked about the ionic strength, which is mentioned in your homework for this week. Now, ionic strength is a parameter which comes from analytical chemistry, actually. And it has similar dependence of the concentration as the Debye length. So the ionic strength is defined as 1/2 of the sum of all ions, the concentration of all ions in solution, times the charge of the ions squared. It measures in moles. Now, one useful formula which you can use to calculate the Debye length is this one, which relates the ionic strength and the inverse Debye length through just one parameter here, and you get the result directly in inverse nanometers.
Why does it have infinity sign on it?
Which one?
Why the concentration?
The concentration infinity means that this is the equilibrium concentration in solution. This is the one which you actually add.
What is 3.288 composed of?
It is composed of, if you think about that, essentially if you express this formula to read ionic strength, and then you bundle all other parameters and calculate them in nanometers, then you get 3.228 from all the other parameters bundled in the right dimensions. So when you plug in the ionic strength, you can actually immediately obtain kappa in nanometers. And this is very useful formula because here you have the concentration of ions per cubic meter. And this is not a dimension that you like to work with. And here you have the concentration of ions in moles. Now again, just because not everybody here is familiar with similar types of calculations, now let's say you have calcium chloride. You dissolve calcium chloride in water at a concentration of 1 moles. Now the concentration of calcium ions is going to be 1 moles. What is going to be the concentration of chloride ions? It's going to be 2 moles. Because you have calcium, 2 chloride ions. So when you do that, actually you have to, when you calculate the concentration of ions, you have to take into account how many ions you have per mole of substance which you dissolve. Just make sure that you put the right concentration of ions. Otherwise, this is very straightforward formula. It immediately gives you the Debye length, the simplest way to get the Debye length. So we know that. Then the other thing that we also studied and derived was the potential distribution. Yes, Karen?
In the last formula, all the salts are in water. This is for the aqueous solutions, Debye length calculation.
What you mean the sign here?
No, the Debye length equation. Is it for aqueous solutions?
For aqueous solutions? Well, in principle.
Or is it for anything? Because
in principle, it would work for anything.
Because we have like the dielectric field of the medium into the equation.
Right. In principle, it will work for anything, but I mean, in reality, you don't use it for many more liquids than water. In reality, the electrostatics interactions are typically important in water. If you start calculating this with oil, you can dissolve many ions into the oil. To be precise, I mean, you can dissolve ions in the oil at all, or very small concentration. So maybe you can have this for some more exotic liquid like formamide. It's going to work for formamide too. But I mean, usually you don't work in formamide, you work in water. So we have the distribution of the ions away from the surface. This is the actual calculation of that distribution. And you also have the potential from the surface decaying when you go further away from the surface. So last time we also derived the expression for simplified expression at low potentials for the potential decay away from the surface. So the potential at any point x, which is actually shown here, is going to be equal to the potential on the surface, which is this one, times the exponent where you have the distance divided by the Debye length. So the Debye length is actually the parameter which tells you how fast this potential and the concentration of ions decay away from the surface. Now, one useful formula which we are going to use just in the next transparency is the relation which we derived previously, actually it was on the previous slide, between the surface charge and the surface potential and the Debye length. You can substitute the surface potential here with the surface charge, and you have this equation which gives you the relation between the potential. Now 0 here should be x actually. I mean, I've put in 0 because this is already the form which we're going to use in the next slide. But the relation between the potential, the surface charge, the Debye length, and of course, this is multiplied by the exponent. Now, one distinction that you should make from here on is whether the formula that we derived use surface potential or whether they use surface charge. Why is this important? Because in many cases you're going to see that it makes a difference if you do exact calculations. So in other cases you need to know, for the system that you're studying, you need to know what you use. Whether you have data for the surface potential of the particles, which you obtain by electrophoresis, which you're going to study later, or whether you have data for the surface charge of the particles, for example, which is usually obtained by titration or you obtain it from the producer. So when you buy latex microspheres, for example, a good producer would also tell you what is the surface charge density of these microspheres. So that's why this formula is useful, because you can plug the surface force, the surface charge density here. And then, now let's go to the new stuff here. Just a couple of slides so we can derive the formulas that we need. And then we're going to explore the importance of these formulas. Another formula which we derived last time is the relation between the pressure between the surfaces and the density of the ions in the midplane. Now, again, this is it's a little bit complex, so let's try to kind of understand this formula. Density of ions in the midplane and density of ions in the midplane at infinite separations. So essentially, in order to use this formula, you have to know what is the density of the ions in the midplane when you bring the surfaces close. And out of this density of the ions, you have to subtract the density of the ions when the surfaces are infinite distance away. And physically, this formula is essentially an osmotic formula. It works like that. You have, let's say, the counter-ionic atmospheres close to the surfaces. They are equivalent to increase of the ionic concentration. So when they are far away, nothing happens. The system is electroneutral. We don't have electrostatic repulsion. When you bring them closer, the system remains electroneutral, but the two increased ionic concentrations start overlapping. And this overlap essentially leads to osmotic force. You can't push ions against each other. You can't concentrate ions without spending some energy. So this is the origin of the repulsion between the interfaces. So we have done electrostatic calculations, but in the end, we're using the electrostatic calculations in order to express the density, the concentration of the ions in the midplane between the surfaces. And then this is the formula that we need in order to calculate the pressure or the force. So if you remember last time, actually you have it as a part of your homework, we derived this relation between the density of the ions at finite separation and infinite separation. And what you do is you put the Boltzmann formula here. You take the exponent. You actually expand the exponents in series. You take the first three terms, out of which only the third term remains. So that's why you have the squares here. And we can substitute this formula here inside the formula for the osmotic pressure. So the pressure is going to be, if you substitute this formula, is going to be this one, and then if you do all the simplifications, it's going to be like that. So the pressure, the electrostatic pressure between the surfaces is going to be equal to the, this is a constant electronic charge, the charge of an electron. The potential in the mid-plane, the potential here, 2 times kT, and the density of the ions at infinity. So the only thing that we don't have in this formula is what? That we still need to calculate. Which of those parameters is unknown yet? Sorry?
The potential at mid-plane.
Right, exactly. So out of these parameters, we don't know the potential on the mid-plane, because what we know is we know either the potential or the charge on the surface. So what we need to do is we need to explain the potential in the mid-plane via the potential on the surface. And we know the formula for that because we have derived it in the previous slide. This is this exponential decay. Now the point, however, is like that. Now we don't know what happens when with the potential when the two surfaces overlap. How does the potential change? Because you have the potentials from the two surfaces acting in the mid-plane. And the simplification that people have used is called superposition approximation, and it tells you simply that the potential in the mid-plane is going to be 2 times the potential of the two surfaces if they were at the same distance but further out. Now this is very important, so try to understand that. If you have problems, ask me. But let's say the other surface was not here. We calculate the potential at the distance between the surface and the mid-plane without the second surface present. Then we bring the second surface to assume that the potential here is going to be 2 times the potential that each surface generates. So we assume that the potentials are additive. If we assume that, then we can put in this potential in the mid-plane to be equal to 2 times the potential at the same distance but without the second surface, calculated by the decay length that we know. This expression transforms into this one. I'll let you ask questions in a second. Let me finish this derivation. This is the same expression that we have derived already. The potential for one surface at the same place when at infinite separations. We need to express this potential in the point x, which is the distance, half of the distance between the plates. So we use the formula that we have already derived to use the expression that has the surface charge. We just put in here x equal to d over 2. This is the distance between the surface and the mid-plane. We put both of those surfaces, both of those formulas together. We obtain this formula where we have essentially kappa appearing here in the divisor. We don't like that. We can substitute the formula for kappa here, and after lengthy but straightforward derivations, we obtain this final formula. I'm going to even, it's easy to write with the mouse, I'm going to even put a smiley face here, because this is the formula that we have been looking for since the beginning of the previous lecture. So we have gone through all derivations, and we have finally derived a formula which gives you the pressure between the two surfaces as a function of the surface charge density, as a function of kappa, and as a function of the distance between the surfaces. So it connects everything that we have experimentally and that we need to know for the colloidal surface. It connects the surface charge density, it connects the epsilon of the media, which is typically water, the distance between the two surfaces, and the ionic strength. it tells you how, when you add ions, the electrostatic interaction between the surfaces is going to change. Once we have this formula, it's straightforward to integrate it by the distance and obtain the similar formula for the energy of interaction between unit areas of identical surfaces. Just some kappa here appearing in addition to the other formula, and that's it. Now, let me remind you that this formula, however, was derived at the assumption that we have a low surface potential. So we could actually use the expansion in series at one point in the derivation. So this is not an exact formula, it's an approximate formula, but it is a very simple formula and it's exactly what we want for calculating electrostatic interactions. And I'm going to give you the exact formulas a bit later, but let's kind of stop a little bit here and let me see if you have any questions about the derivation or how electrostatic works or something like that. Daniel.
Is the force of attraction accounted for in this equation?
No,
the
the force of attraction is the van der Waals force, right?
That's what I'm just talking about.
We're going to add it just in a few minutes. Right now we're deriving the force for repulsion. And you're going to see that when we combine the force of attraction and repulsion, we're going to get lots of interesting things. Right now what we want to do is we want to derive an equation which tells you, okay, I know about my system, I know what do I know about my system? I know the surface charge density, I know how much electrolyte I have added, and I know what is the distance between the objects. So let me calculate the repulsive force. And you can do this straightforwardly. So that's how it works, yes?
25 millivolts, does that come from EV?
25 millivolts comes from, you want to compare actually what you have here in the exponent of that. Actually what we have done at some point, let me see, I'm trying to find it where we had that. Yeah, so you have we actually have we have used an expansion of series of this formula. Now we assume that the z is equal to 1. Now this one, the parameter in the exponents has to be smaller than 1 or so in order to be able to use an expansion in series. So that's why essentially E psi has to be equal to kT. There is a parameter of 4 which appears at some point, but it appears when you do the derivations actually. So that's how it comes. So 25 millivolts, if you know, is also the value of kT at room temperature. So we're fine. Okay, so we have derived the pressure and the energy between flat surfaces. Now we need to do the same for particles. And we have taken some time and pain in one of the previous lectures to derive the so-called Diriagin approximation. If you remember, when we derived that, we discussed that Diriagin approximation is very useful because you can, once you have the energy between flat surfaces, you can immediately obtain the force between curved surfaces, between particles. So this is the formula which we derived just on the previous slide. Diriagin approximation tells you, I have added this sphere just in the last moment, that the force between two spheres is equal to pi times the radius times the energy of interaction between unit surface of flat surfaces. You remember when we derived that a few lectures ago. So we don't need to derive anything else, we just need to put in this formula for the energy, in the formula for the Diriagin approximation, and then we obtain the energy of the force and the energy of interaction between two spheres. You see that here we have the radius appearing. We have kappa again appearing in the bottom and so on. Again, we remember that when we have been deriving these formulas, we had this series expansion. So this formula is valid for small potentials.
Does this mean it is valid only for 1s2 electrolyte also?
Actually not, because when we have been deriving it, I think now I showed this selector, this Z when we have been about the expansion. But actually, if you do the derivation, the charge of the ions does not appear anywhere in the series. So this formula is true for any type of electrolyte,
Or do you?
but it is true for only small surface potentials.
We neglect the third order terms, right? Terms after 3. I mean, in the expansion of this e power x, right?
Right.
So we take only first 3 terms. If you take the rest of the terms, there z is.
Well, that would be the exact expression, but this formula would approximate fairly well the effect of the electrolyte, regardless of the electrolyte. What it can't approximate well is the repulsion at high surface charges. So it is fine in terms of the electrolyte, it's not fine in terms of the surface potential. We have not done assumption for the electrolyte in deriving this formula. That's why kappa appears as kappa. Otherwise, if we had done an assumption for the type of the electrolyte, we wouldn't have kappa here. We could have substituted this for directly with the concentration of the electrolyte.
Yeah, right.
And actually, this relates to your homeworks and any calculation that you have to do in the future. If you open useful books like Izrevashvili's, you can find directly formulas which tells you what is the relation between the force, the surface charge, and the distance for 1 electrolyte, 1 2 electrolyte, and so on. So good people have actually again derived these expressions for different types of electrolytes. This is the general formula, but you don't have to calculate kappa in many cases. If you have a single electrolyte, you are likely to find the formula already in the literature. Now, if you have a mixture of electrolytes, of course, then you have to calculate kappa because you don't have formula, other formula that gives you mixture of electrolytes than this one. So we have these formulas, and using them is straightforward. You don't have anything else, just simple calculations, and you can calculate force. And so far we have been deriving these formulas for low potentials, but then people have been good enough, and that's not that difficult. We just don't need to spend time now in the class. Have derived similar formulas for any potential. Now, first of all, you have the formula for the potential distribution away from the surface as a function of the distance for the case of the exact solution of the Poisson-Boltzmann equation. This is called Gouy-Chapman expression. Now, you say, oh, that looks even simpler than the previous one. But then this parameter gamma here is actually a hyperbolic tangent of the potential here again, and so on. So actually we have hyperbolic tangent of the potential times the exponent of the kappa and the distance. This, however, does not make this formula much more difficult in terms of calculation. You just put in the formula in a calculator or in a program, and you still can calculate electrostatic repulsion. Just remember that gamma here is a parameter which in itself includes an expression which includes the electrostatic potential. And then when you do the exact solution, then this is what you obtain for the pressure between two surfaces. This is what you obtain for the energy of interaction per unit area. And this is what you obtain for the energy of interaction between two spheres of radius r. Let's do just a little bit of analysis here and answer questions. Now, if you compare the formulas for the interaction between the energy of interaction between flat surfaces and two spheres, the major difference that you see is that kappa here is squared below the divisor, which tells you actually that the dependence on the electrolyte concentration is stronger when you have spherical particles rather than flat surfaces. And this comes because you have a smaller overlap of the counter-ionic atmosphere when you approach to spheres. So the osmotic force actually decays faster than in the case of two solid surfaces. This is not, of course, surprising or unexpected, but this is just something that you can keep in mind, of course. And this is what we can derive in terms of formulas. People have made even more complex formulas for more precise expressions. I'm not going to give you the more complex formulas. I just want you to understand a little bit of the physics for the more complex cases which you can find in reality on the next slide. But before that, let me see if there are any questions so far or any point for discussion.
I've got a simple question. What are the units in volts? Is that energy over charge over coulombs?
Volts is actually the equivalent of, let me see how the units would go. KT actually can be expressed in volts, so it's the equivalence of energy. They have the same basic dimensionality.
Volts and energy? Volts is joules per volt.
Maybe, but
Electron volt is energy. Yeah.
right, but when you have KT, actually KT can be expressed in millivolts.
That's electron volts.
Electron volts.
Maybe electron volts. I mean, I have to check. I mean, like there may be one dimension different, but I mean they're equal. I have to check. You have to take care, of course, that the dimensions are right in this case. But volts typically is not I don't think it's a basic dimension in SI, so you can express it through other dimensions. So that's why it would appear as some meters, seconds, and newtons, and you need one electrostatic parameter, which is usually the current, A, the charge, coulombs. So coulombs are going to appear someplace. They can be kind of course, know that this here. Okay, yeah, that's. I mean, you're right about the electron volts. I mean, like essentially, psi s is going to have times E is going to have a dimension of KT. So, I mean, essentially, E already, like when you multiply by E, this is essentially the conversion from electron volts to energy. So this is the one that fixes the dimensions between volts and energy. Any other questions, Daniel, or that's it?
Can you use the argument expression for this case? Wouldn't the cloud sort of change when you have two spheres? The cloud would just go to the other side and change the whole thing?
You mean like what would happen if you use the Raleigh expression and take this formula? Actually, I have not put the formula for the force here, but I'm pretty sure that if you just take this expression and just multiply it by pi r, you're going to get the formula for the force between two spheres. That's how the Raleigh expressions work. I haven't.
Does it apply in this case because you're changing the interaction if you put the ions on the other side, which you couldn't do in the first case, but which is going to happen in the second case, right?
Well, yeah, but I mean, yeah, in a way, but this. I mean, let's put it this way. I mean, just to cut it short. I mean, the Raleigh expression would still apply. I mean, that's its power, and again, the Raleigh expression is always an approximation. But all these formulas that we have an approximation. And actually, your question is, in a way, a very good introduction to my next slide, which shows what you have in real systems. Now, all those formulas that we have been deriving so far really do some approximations, and even the Raleigh approximation in itself is an approximation. Now, what is going to happen if you take your formulas, if you calculate the repulsion between two plates, and then start bringing the plates closer, and you have essentially here, this is dimensionless surface charge. Dimensionless means that it is going to be equal to 4 times kT over E. So this is, in terms of volts, this is 25 millivolts, and this is going to be 100 millivolts. So this is, again, like in, now, this is a good point actually to just give you the typical charges and the voltages. Now, typically a colloidal system would be charged somewhere between 0 and 100 millivolts. Charge, I mean potential, would have a potential of between 0 and 100 millivolts. You can have systems which have more than 100 millivolts, but these are really exotic systems. And you don't really go somewhere above 150 millivolts or so. 25 millivolts is really the boundary for small repulsion. Charges below 25, potentials below 25 millivolts really don't stabilize systems usually. So latex particles that you're going to buy or gold nanoparticles that you synthesize and so on would typically have a potential between 30 and 90 millivolts. And to discuss how you measure this potential a little bit later in the lecture on electrophoresis. So there is a way to measure that. Yes?
What kind of surfaces, or what's a property of a material that will represent what kind of charge it will have on the surface?
The number of groups per surface area.
I mean,
the property
an
of
intrinsic property of the material that is accumulating charge on the surface. What?
Well, that relates to what we have been discussing. Why do you have charges in the surface in the first place? You can have ionizable groups. You can have species from solution adsorbing and so on. The point, however, is that you can charge a surface infinitely, because if you start charging it too much, you're going to have charges too close to each other. So naturally, whatever you do, you can't really push the charges so dense that they're going to have potential much beyond 100 millivolts. Just nature wouldn't allow you to do that, because that's lots of energy to put in terms of charges on the surface. So that's why most typical suspensions would have a surface potential between 0 and 100 millivolts. And then this is what happens if you calculate the force by using the formula that we have, and if you do actually the real experiments by starting kind of bringing those surfaces together and measuring the force. Now what you're going to see is that really nothing much, there is no much deviation between the formulas that we derived and the actual force to, let's say, for small potential, an area which is about, let's say, 3 times kappa, 1 over kappa. And so this is kappa times h. So this is essentially 1 times kappa, 1 times over kappa, 2 times over kappa, 3 times over kappa, and so on. So this is the dimensionless distance in terms of kappa. Kappa is the unit of dimension here, because as we described, kappa is the one which controls the behavior of electrostatic system. And for highly charged surfaces, actually, you have to go below 1 kappa in order to notice some significant deviation between the real system and the formulas that we have derived. However, anytime you go too close to the surface, suddenly you see that the actual potential and the actual force and the force that you are going to measure start deviating. Physically, this means that you are really pushing those surfaces too close. You are having those ions really being very concentrated. The potentials are very high. You have lots of energy concentrated there, and all those linear formulas are failing. And then you can find out that in nature you're going to have 2 cases. The force that you're going to measure can be lower than the theoretical force, or it can be higher than the theoretical force. And the reason for that is that because you have 2 different physical cases that can happen in real system. You can have constant charge on the surface, or you can have constant potential on the surface. So when you bring the surfaces at constant charge, means that they're going to keep the same number of groups on the surface that they have at infinity. When you bring them at constant potential, this means that at some point the potential is going to start the potential is going to kind of like remain constant, and then the surfaces are going to decrease their charge in order to not allow the potential go further than that. Kind of in a way, you can think of this being a hardliner surfaces and this being a kind of more softliner surfaces, in the sense that this one wouldn't let their charge go. You can bring them very close and they will still keep the charge and they will still repel each other. Well, these surfaces in a way make a little bit of a compromise in allowing the potential to stay constant, because they wouldn't want to really go to two very high repulsive forces. This is just, if you remember, this is the relation between charge and potential, which actually breaks down in this condition. You can imagine that if you keep the potential constant, when you bring the surfaces closer, the charge actually is going to decrease, because the potential will be, you have potential from two surfaces acting on the surface. So in reality, the surfaces which have charges which, now let me give you some practical example of those systems. If you have really strongly charged groups on the surface, like sulfate group, a sulfate group would be ionized no matter what. You can bring another sulfate group very close and the sulfate group is going to hang on there and stay. Now imagine, however, that you put some surfactant on the surface and the surfactant doesn't stick very strongly to the surface. If you bring the two surfaces too close, the surfactant is going to be uncomfortable there, so it's going to start dissolving and actually moving away from the surfaces. So beyond a certain threshold, the surfactant is really going to start leaving the gap between the particles. So that's why the force actually is going to be smaller than the force that you would expect to determine theoretically. Or otherwise the force is going to be stronger, because the potentials overlap so much that no linear approximation is valid. You have highly nonlinear, strong electrostatic repulsion. Now, hopefully you won't have to really consider this too much in your practice, because as you can see, this is really happens when you bring the surfaces close. So for just understanding particles, suspensions, and many other systems, you don't really have to go to these very complex to calculate and measure cases. Hopefully the linearized formulas should be okay. You just have to keep this in mind.
What's the y-axis? Is that KT and?
The y-axis, this one is normalized force.
Okay.
So this is dimensionless force. This one is dimensionless distance in terms of normalized by KT. So this is just the very same force versus distance dependence that we have been studying, but just is plotted in dimensionless units, like theoreticians like to do. So it's valid for a wider variety of systems. Okay, any questions? We're going to come to electrostatics in the second slide. Now, this is an explanation of one slide presentation of everything that we have studied so far in the last 5-6 lectures or so. And this is essentially the one which tells you everything that you could know about the colloidal system by using electrostatics and van der Waals. Now, this is the famous Diraguin-Landau-Verwey-Overbeek theory, which relates the repulsive electrostatic and the attractive van der Waals force. So there were a couple of guys in Soviet Russia and a couple of guys in USA who came up to this independently, and this was during the years of the Cold War. So after some time they were kind of surprised to find that somebody else has done this, and in the meantime some people had called this Verwey-Overbeek theory, some people have called it Diraguin-Landau theory. So to reconcile this, they call this Diraguin-Landau-Verwey-Overbeek theory.
Which ones were the Russians? Which ones were the Americans?
Diraguin and Landau were the Russians. Perveyev over Bick were the ones working in US, I guess. I mean, they may not have been US born or something like that, but now the Ryagin is, if you remember, we discussed the Ryagin's approximation and so on, the famous scientist who really lived very long. Landau is, the ones of you who have studied physics may have heard the Landau books of physics, which is a very basic, very fundamental reference, but not one that you want to study from, actually. It's really very hard theory for any level, unless you're a really theoretical physicist. Anyway, so these two groups of guys independently came up with the same theory, and it tells you like that. Now you have electrostatic repulsion, you have attraction. So what you could do is you could take very much and plot them on the same curve. Now, if you plot the energy as a function of the distance, you can have repulsive energy or attractive energy. The repulsive energy is going to be the electrostatic one, so you can this is how it looks as a function of the distance. This is the formula which we just derived. Previously, we also derived the formulas for van der Waals attraction, which is like that. It's not really a good way to show with that arrow moving. So now if you compare how these two forces actually go, you're going to find out that the electrostatic energy is the longer ranged one. So the electrostatic energy takes off first. However, the van der Waals energy, which starts slowly, actually when you come to cause a separation, becomes predominant. It's stronger than the electrostatic energy. So then when you add these two energies, in the case where they are approximately balanced, you are going to find out actually the van der Waals energy is a little bit stronger here, the electrostatic energy is a little bit stronger here, and then the van der Waals energy becomes a little bit stronger here too. So eventually the interaction between the particles is going to be attractive at long distances. Then suddenly you have this strong attraction because of electrostatics. And then suddenly when you go a little bit further, closer, you are going to have the van der Waals being stronger again at very short distances. So the interaction again becomes very attractive and the particles jump into contact. Let me now what this means from the viewpoint of a particle is that you are one of the particles, you want to be here or here, and you don't want to be here. Now, in order to jump here, which is really the one you like, you want to minimize your energy. In order to jump here, however, you have to overcome this energetic barrier. If this energetic barrier exists, you will not be allowed to really jump into that favorable spot, just because you have to jump over this energetic wall. So if you sum up everything, the particles would like to jump into contact. Because if they do, they are going to have this very strong van der Waals attraction, and they are really going to be at the minimum of their energy. Until the moment when they touch, of course, when they are going to have hard body repulsion. However, they are not allowed to do that because electrostatics keeps them a little bit further apart. There may be some small attractive interaction here, which I'm going to come to this later, but it's not that important. What is important is the electrostatics keeps the particle further apart than the van der Waals would bring them into contact and irreversibly coagulate them. The bottom line here is also this energy is so strong that if you allow the particles to jump into contact, they are never going back spontaneously by themselves. And this is just how this is called. This is called secondary minimum here. This is called the energy barrier. And this is called the primary minimum here. Now, what is the cute thing, and we're going to study it quantitatively a little bit later, is that you can change the Hamaker constant. Hamaker constant is a Hamaker constant. The only way to change it is to change the environment, which you don't do typically. But you can change the electrostatics very easily by adding electrolyte. In all those formulas, actually I have put in the formulas here. when you increase copper both here and here, you actually have the repulsion going down. When you dump electrolyte, the electrostatic dies. So then, these are the different cases where what happens when you control the electrostatics by adding electrolyte. Without electrolyte, you have very strong, very long-range repulsion. And this is the reason why when we deionize latex, it stays long, long distance away from each other. When you just add a little bit of electrolyte, which typically happens in room conditions by SO2 dissolution, you are going to have, this is the typical case which you have in practice, like curve B here. So the two particles can come relatively close to each other, but they are separated by electrostatics. And then when you keep dumping electrolyte, you're going to reach a point where the energy barrier is going to disappear. There is nothing which is going to keep the particles away from each other. And then they're going to simply jump into contact by the van der Waals forces and aggregate. And this is exactly what is seen in practice, and we'll discuss this a little bit later. But right now, this is very important, so this is the time to ask questions and really understand this well. Brian was first.
Is it? I guess I'm a slide ahead. Sorry.
Okay. Oh, you're reading my next slide, and you're asking questions on that already. Okay. Daniel had a question.
How can I follow that? What I'm confused about the electrostatic repulsion.
Uh-huh.
Because before we're talking about osmotic repulsion.
Right.
So.
Right. It's always osmotic. When I say electrostatic repulsion, I mean that it's electrostatic by cause, not by physics. So when I say electrostatic repulsion, this means repulsion because the surfaces of the particles are charged. We know that this is actually equivalent of an osmotic repulsion, but it's much easier immediately to understand that this comes from charges. And we're going to discuss some other osmotic effects later. So, osmotic is very dangerous in this case because you can get confused with other types of interactions. So when I say electrostatic, it means caused by surface charges.
Can I follow up on that?
Right.
So as you add electrolyte, does the repulsive force go down because the distribution becomes narrower, is closer,
Right.
There's more concentrated near the wall?
Right. Physically, what happens, you have all those ions which immediately kind of in a way saturate the electrical field. So, they really get to be close to the wall and there is no osmotic repulsion at large distances. Now, how this works in the formulas, you can see here, this is the expression for two spheres. You remember that kappa, okay, I shouldn't try that. Kappa was a function of the electrolyte. The more electrolyte, the larger the kappa. Now, if kappa is here, then the larger the kappa, the smaller the repulsive force. And this is only one side of the coin, because you also have kappa here in the exponent. The larger the kappa, the faster the decay. So when you add electrolyte, what happens is, I'm going to show actually, it's on the next slide. That's actually, immediately you can see this is experimental data. No, actually this is for charge. Okay, I have some of those a bit later. This is the case what happens when you add electrolyte. So the more electrolyte you add, the electrostatic force first of all gets to be smaller, and second of all decays faster. So both the height of the energetic barrier and the, let's say, outreach of the energetic barrier decrease when you add electrolyte. And at some point you're going to reach the point where you have no barrier at all, and then everything clumps together and precipitates. I'm actually going to show some experimental data of how this works. Any questions on this curve before that?
extra minus sign on the equation.
Well, what do you mean? You mean that you have minus sign here and here? No, the idea is that actually the equation is continuous here.
Okay.
The point is that they work in different directions. So I go explore this expression immediately afterwards. Let me show you how it works in practice. These are data which people have measured by using the Izrevashvili surface force apparatus. And the first one actually shows how the force versus the radius, this is force versus radius because you have two cylinders, which is the equivalent of energy actually, how the force versus the radius changes as a function of the distance. And what people have done here, they have used sapphire. Sapphire changes its surface charge as a function of pH. The lower the pH, the closer you to the isoelectric point, which means that there will be no charge at all. This is the case of different charges. So you can see that what people have done here, they have changed the pH, and they have measured the force versus distance curves. So what happens here is at large pH, you have large charge, and the surfaces repel each other strongly. Smaller pH, smaller charge, smaller repulsion. Even smaller pH, even smaller repulsion. And then I told you that about 25 millivolts or so, the electrostatic repulsion really becomes pathetic. And you can actually see this here. At 20 millivolts, the energetic barrier is, really doesn't look much like a barrier already. So the point, of course, and people have been very excited about such data, because the Izrevashvili apparatus has been the first of all the people really to measure these DOVO forces, which by then have been described only theoretically. So it has been the first means to actually you can take two surfaces and you can measure the force, and you can compare it with theory, and people have been very excited. These days, in the era of AFM, the excitement is not that large because everybody can measure it in his lab. But still, DOVO theory has been considered one of the most significant achievements in colloidal science. Because it's very simple, but it describes well some of the properties of the system. We are going to discuss the other properties that are not related to DOVO in the next lecture, what are the other types of forces. And when it comes to nanoscale engineering, actually, the other forces that we're going to study are more important because some other forces allow better control. In a way, the basic about nanoscale engineering is how to control the forces and interactions. And to discuss ways to do that. Raj?
Do these curves change the behavior if your surface is oppositely charged? Instead of negative, it is positive. Then if you change the pH, then the
nothing would change if you change if you have the same surface potential, but if you just change the charge.
Yeah, let's say instead of negatively charged to negatively charged.
They're exactly the same. They're exactly the same because you can see what appears here. In the formula, you have kappa, and kappa is not kappa is a property of the solution. It's not a property of the surface. So and here you have now where is the charge here. Where is the potential? If you remember, this parameter was a hyperbolic tangent, which includes the surface charge. But it's squared, so whether it's positive or negative, it always has exactly the same result. So whether they're positive or negative charges doesn't matter. Now, if they are oppositely charged, one positive, one negative, then as you can imagine, the result is disastrous because you have one sign is going to flip somewhere, and the force is going to become immediately attractive. But surfaces of same charge really have the same repulsion, regardless whether it's positive or negative charge. Daniel had a...
Yeah, if you get an electrolyte solution in between these surfaces, isn't it going to sort of distribute the positive and the negative ions in the electrolyte to equal out the charges on each surface?
Sure, but
we're talking about the Helmholtz layer now? Is that what Raj is talking about?
The counter-ionic layer. We haven't defined Helmholtz layer. We're going to do this a little bit later. But the counter-ionic layer is really going to be symmetric. In one case, the positive charges will be close to the negative surface. In the other case, the negative charges will be close to the positive surface. But everything is going to be exactly the same, just the situation, the distribution of charges changes, but it's going to be the same.
Okay, so I mean, are we talking about some sort of molecule charge that's absorbed to the surface?
No. I mean, like right now, there is no absorption. We have charged surfaces and we have electrolyte. The charges on the surface may be by absorption. What the question here was whether anything is going to change if you just inverse the charges. Now, how do you inverse the charges is just a theoretical question now. I can tell you how you can do that. And this happens in reality in many cases, but right now we're just considering the consequences of the formulas. Now, this is what I have been telling you so far. You take a suspension, you add electrolyte, Q of the electrostatics, and then the suspension is going to start aggregating. You have certainly seen similar phenomena. We're going to discuss some biological consequences of that, but in any case, going to start aggregating. Now, how does the electrolyte and the Hamaker constant affect the interactions? These are theoretical curves when you increase the electrolyte. Energy as a function of dimensionless distance. Low electrolyte, high repulsion, long range repulsion. More electrolyte, lower repulsion, shorter range repulsion. Even higher electrolytes, nothing can hold the particles apart, so they stick into contact. I mean, essentially, here what the particles are going to do is they're going to immediately jump in this energetic minima. If somebody is a little bit unfamiliar with all those energy curves, you can consider always when you have a curve like that, you can consider the behavior of the particles. Imagine that you have a small kind of balls and you put it someplace. The way the ball is going to roll and where it's going to stop is exactly what happens with the particles in energy. So if your ball is here, it's going to roll on and stop here. If you put your ball here, then your ball is going to go back here. That is the repulsion. If you put your ball here, I mean, then it goes directly down there and never comes back. So this is the effect, what happens when you can change the Hamaker constant. You can see that when you increase the Hamaker constant, actually the potential of repulsion becomes attractive, and it kind of sucks in the particles in the gap. Actually, the way the Hamaker constant works here, this is the low Hamaker constant, this is high Hamaker constant. But you can see that eventually for low attraction, low Hamaker constant, you need to add quite a bit of electrolyte in order to kill off the repulsion. If the Hamaker constant is high, even a small amount of electrolyte will be more than enough to bring them into contact. And then, even if we don't finish this lecture, this is important, so I want to understand it. People have derived the criteria for stability. Now, the original scientists which did that really did an approximation. So the way they defined the criteria for stability was like that. Now imagine you have electrolyte, you add some electrolyte, you keep on adding it. At high electrolyte, you're going to have high repulsion. You add more electrolyte, the repulsion becomes smaller and smaller and smaller. And then at some point, this energetic barrier is actually going to hit the zero axis. So you're not going to have repulsion at all. Assume that this is the moment when the system becomes unstable. Now, if you have followed my lectures, you're going to tell me, no, you have been telling us something else. The moment the system becomes unstable is not the moment when this is zero, but it is the moment when it is what? What is what? What should be the energetic barrier here for the system to become unstable? What's my favorite thingy? Favorite estimator, parameter? KT, yeah. If this barrier is lower than KT, then the thermal energy is possibly going to be sufficient to kind of push the particles over the barrier. Now, from the viewpoint of practical purposes, however, KT is really a very small barrier on that scale. And it complicates the formula, so people have just assumed that this is the case where the system is going to coagulate. This is the case where the particles which have been stable are going to suddenly jump into contact and precipitate. And how can you describe the system? Well, we have this joint potential which has the electrostatic energy, repulsive, and the van der Waals energy, attractive. The moment of instability is actually the moment when this here point, the function in this point, both the function and its first derivative becomes equal to 0. So what you have here is, this is the equivalent of a system of two equations. One is that this one is equal to 0, and then the other one is the derivative of this equation is also equal to 0. If you have this fulfilled, then your system is going to start precipitating. So then you can substitute, and different college books actually give you different values of the parameters here, just because people use different expression for electrostatics and so on. Now this is the one which I derived myself. So you have a very, very widely different range of parameters here. Now what is important, however, is you are getting to, from the first equation, you are obtaining the critical distance, if you call this critical distance, which once crossed, the particles can never go back. So this is the distance where if you bring the particles closer than that, they're just jumping in here and never coming back. So the critical distance is equal to, surprise, surprise, 1 over kappa, equal to the bi-length. So if you bring the particles closer than the bi-length, they're going to aggregate and never come back. The second one is that the critical concentration, which is obtained when you substitute, let's say, for different types of electrolytes, assuming that you have a electrolyte of different charges. If you substitute for in the expression for kappa and then derive all the expressions, so there is lots of derivation here. You can do this if you like long derivations. But this is the relation between the concentration of electrolyte, lots of parameters here, the surface potential, Hamaker constant, and then this one here, which actually is the charge of the counter ion to the 6th power. Now, it's very difficult to check these parameters, and it's very difficult to check the other dependencies. But it's very easy to check the relation between the concentration when the particles are going to start aggregating and the charge of the counter ions. So what you could do is you could start, let's say, you can take sodium chloride, calcium chloride, aluminum chloride, and measure the concentration that is required for aggregation of a suspension. And if you do it theoretically, you find that this is dependent on the inverse 6th power of the charge. And when people derive that, they have been very happy, because some guys called Schutz and Hardy, I hope, or maybe it's one guy, I'm not quite sure, have already found this relation between the critical concentration and the charge of the ions. Now, if you kind of read behind the formula here, you're going to find something very interesting. It tells you that if you, let's say, change from sodium chloride to calcium chloride, you have an immense increase in the efficiency in terms of precipitation and aggregation. If you go to aluminum chloride, you have even much stronger increase. So if you want to aggregate a certain system, the bottom line is don't use sodium chloride, use at least calcium chloride or aluminum chloride. And actually these are just examples from experiment. Now this is derived in the approximation of strong potentials. These are data from literature. You have to add 50 to 58 millimoles of monovalent ions in order to precipitate some suspension of nanoparticles. Now SAW actually is a suspension of nanoparticles. People didn't know that nanoparticles would be so fashionable one day, so they call them SAW, but I mean this is actually nanoparticle suspension. If you use divalent ions, again you can see that the concentration that you need to use is not so much dependent on the ion. So you can use magnesium or zinc, calcium in many cases. It's about the same. But then the relation between the monovalent and divalent is enormous. You have 2 orders of magnitude difference in the concentration that you need. And then if you use trivalent, I mean you need even less than that. And it very well matches the Schulze-Hardy rule. So this works fairly well. This is an expression for large potentials, but it works well. Now let me give you a question here. Why do people, anytime when people actually purify water? So the first step if you take water from a creek, the first step in purification of water is dumping aluminum chloride inside the water. Now why is that done?
Get out particulate matter.
Right. Any particulates, biological cells, whatever you have colloidal in water, is going to kind of immediately aggregate and precipitate and so on. So this is the way to clear the water. Now you have to do additional purification afterwards, but just from colloidal viewpoint, removing any type of particulate, including biological, in water, is most efficiently done by using a trivalent ion. And aluminum chloride is fairly benign substance. Its solubility is low, it hydrolyzes. So once you do that, I mean you can purify water and you can drink it. Now, however, you know from colloidal viewpoints why the water becomes, why don't you dump sodium chloride, for example, to do that? I guess in spite of colloidal, you can think of other reasons why you don't dump sodium chloride to purify water, but anyway. Actually, as a homework, you're going to check the validity of this expression. One final slide here before end. Put a little bit behind time, but we started a bit late. Now, we mentioned this secondary minimum, which is in principle attractive. Now, however, I mean, don't rely on that and don't try to capture particles in the secondary minimum. If you actually calculate, you're going to find out that first it appears in a relatively narrow range of conditions. And second of all, people have found out that it's weak and reliable, and I'm not aware of any place on any real system where it's observed conveniently. So numerous researchers and writers of proposals, especially these days when everybody tries to do something on the nanoscale, have tried to make kind of like use of this secondary minimum. You can write it in a proposal, but then, I mean, it's not likely to work. So this is really something that's theory predicts, has been observed in some rare cases, but it's not a really stable and serious entrapment of particles. And you can see actually the reason here. This is a theoretical calculation for these different systems. Now you are going to tell me why this secondary minimum is pathetic. It's less than kT. So particles entrapped in the secondary minimum is going to jump out by thermal motion. Let's finish here. We have finished with our time. Now, any questions? Brian?
Could you go back to the actual data?
This one?
No.
I think somebody wants to answer the question.
This one?
Yeah.
Uh-huh.
How come you don't see any data points measuring the. That's with the SFA device, right?
You mean how come you don't have any data points here?
Yeah.
Well, because I mean, think of yourself as the poor user of the balance that tries to measure forces. Now, the balance works like by essentially you have a spring which deflects. So you start kind of bringing them closer, and the spring deflects, right? So by the deflection of the spring, you can detect how much they repel each other. Now you keep on measuring, and then you reach this point here, and then you go past the energy barrier. Now what's going to happen? Ping! I mean, they just immediately smack down. So eventually the next point is going to be somewhere here, and that's it. So
I just wanted to know if there was a point.
you can measure, actually these days, you can measure these points by using atomic force microscopy in some cases.
But there is a point. It's just off scale.
There is a point, but well, the problem is that the balance is not able to measure this because the some pieces will jump into contact. Technically, it's not. You cannot measure them by using the surface force separators.
So that's just. They just have an equation that they fit the data points.
Right.
So you can just measure the force which will keep it apart. You can measure
Right.
how much force now you need to apply to keep the surface
Right,
apart.
right. That's how surface force separators work. Okay, let's finish kind of formally.